In this set of lecture notes, we're going to talk about all the preliminaries that we need in order to be successful in doing physics. So we'll talk about sig figs, scientific notation, units, a little bit about conversions, and a little bit about order of magnitude. So let's start with scientific notation. I'm sure that most of you already know this, but it's always a good idea to review. So scientific notation. Now you know that we commonly write numbers in terms of powers of 10. So typically we like really big numbers or really small numbers to be written in terms of powers of 10. So for example, let's take this number here. The way that I would write it in scientific notation is I would write the first non-zero digit, then the period, the rest of the digits, and then times 10 to the power something that would get me back to this number. So for example, this is where my decimal point is. So I go 1, 2, 3, 4. So this means that this is 10 to the power 4. It's a big number, so it's going to be a positive power. Or let's say we take this number, 0.0021. So again, the first non-zero digit, period, the last of the digits, times 10 to the power, and then this is where the decimal is. So I go 1, 2, 3 to get to the place where it was originally. So this is going to be power negative 3 to denote that this is a small number. So big number, positive powers of 10, small number, negative powers of 10. So basically this makes it very convenient and simple to deal with very large or very small numbers. So for example, if I write a number like this, 2 times 10 to the power 30, you don't have to write out basically 30 zeros if you write it with scientific notation. Or maybe something like this, 9.11 times 10 to the power negative 31. So again, you don't have to write 30 zeros in order to express this number. So it's a convenience thing. By the way, that first number, 2 times 10 to the power 30, that is a mass of the sun in kilograms. And the second number, 9.11 times 10 to the negative 31, that is the mass of an electron in kilograms. You don't have to know this, you don't have to memorize it. I'm just giving you a couple of examples of numbers written in scientific notation. Calculations for scientific notation follow calculations for regular numbers. So for example, if you have something like this, let's say 3 times 10 to the power 6 times 3 times 10 to the power 4. So basically, I mean, you can plug it into a calculator just like this. But you could also do it by hand, multiply the 3 times 3, and then combine the bases. Remember that when you, sorry, this is a 4. When you combine exponents like this, if you're multiplying bases, you're adding exponents. So it's going to be 9 times 10 to the power 10. So you could do this by hand or on a calculator. Word of caution, if you're doing something like this, I mean, you can also just simplify the 3's into 1's, that's fine. So you're doing 10 to the power 6, or let's write it as 1 times 10 to the power 6, 1 times 10 to the power 4. If you're putting this in the calculator, either use the EE button. If you don't know how to use the EE button, ask me, maybe in office hours. Or make sure that you put parentheses on everything, especially the denominator. Because your calculator doesn't know that that 10 to the 4 goes with that denominator. So if you don't put parentheses, the calculator is going to just go with regular order of operations, which, by the way, you should also know, but chances are you're not going to be doing much calculations by hand in this class. So when you're doing calculations, just exercise caution. Make sure that if you're dividing by a number written like this in scientific notation, that you put parentheses on it. Or ask me about how to use the EE button. Next thing that we need to discuss are significant figures. People call them sig figs or sig digs for significant digits. I am not really very concerned about significant figures, as in I don't really take points off for using improper number of significant figures. But I also don't want to see 8 million numbers after the decimal point. I don't want to have to read numbers that are written like this. Right? So that I just wasted 5 seconds of my life writing that, and you just wasted 5 seconds of your life looking at me writing that. So let's not waste each other's time, and let's not do that. So that's a no-no. Typically what I do is just keep 3 significant figures in everything as far as problem solving is concerned, tests and such. And maybe for some labs, we're going to use more significant figures. Kind of depends on what we're measuring and what we're calculating, and we can discuss that during lab. So, rules about significant figures. Which numbers are significant? So, all non-zero digits are significant. All zeros between non-zero digits are significant. Okay. Leading zeros are not significant. And trailing zeros are not significant unless there is a decimal point. So those are the rules. So let's do some examples here. 0.0021. Leading zeros are not significant, so it's just these two. So this number is written with 2 sig figs. Something like this, 0.00203. So again, leading zeros are not significant, but 0 between non-zero digits is. Something like this. Trailing zeros are not significant, but these numbers are. And let's say something like this. So these trailing zeros are all significant because there is a decimal point. So typically, I would ask you to round everything to 3 significant figures. Be careful when you're doing homework online on mastering. That might ask you to do 2 significant figures, 3 significant figures, or whatever. There are rules of how many significant figures to carry. So I'll just give you 2 basic rules, but again, I'm very lax on that. I don't really care too much if you follow these rules or not, but I'll give this to you anyway. So when multiplying dividing or doing exponents, you use least number of significant figures. So for example, if I divide, let's say 2.56 divided by 1.2, so the number is 2.133 and so on. So the numerator has 3 sig figs, the denominator has 2 sig figs, so my answer is going to be rounded to 2 sig figs. So it's just going to be this. The rest is not going to matter. So this is actually going to turn into 2.1. You can use this rule if you want, but again, it's not super essential in this class. Now, this next rule is going to be a little bit more essential when we're doing labs, but again, there is only a couple of places where we would have to really pay attention to that. So when adding or subtracting, you use least number of decimal places. Not sig figs, but decimal places. So for example, if I'm doing something like this, 2.56 plus 1.2, so if I did this, it would be 3.76, but this is the number with fewer decimal places, so I have to round to that decimal place, to the tenths decimal place, so this really should be written as 3.8. Okay. So it's all nice and good. You can use these rules maybe in some other classes too. I'm not too concerned about this, but I am very, very concerned about using proper units. And I am very picky when it comes to grading. All calculations should be done with proper units. When you're plugging values into something, they should have units, and the answer should have proper units, and so on. So why are units important? Well, they kind of help you to clarify what you're measuring. So for example, if I say length is 5, what does that mean? Absolutely nothing. If I say length is 5 millimeters, or 5 inches, or 5 miles, then you immediately can at least visualize what's called the order of magnitude. We'll talk about that in a minute. So at least you kind of have an idea of how big that number is. Okay, so units are very important. There are some quantities that don't have units. So when we get to those in this class, I will tell you what they are. But aside from those special quantities, everything has units. So even if I say, for example, there are 10 people in the room, the unit is people. So if I just say there are 10 in the room, that kind of means nothing. That could be anything. But if I say there are 10 people in the room, then it's very clear what I'm talking about. So even some clarifications like that can serve as units of measurement. In this class, we're going to be using what's called fundamental units. And we're also going to be using what's called derived units. By the way, in this class, we're only going to be dealing with SI system. So SI stands for International System, pronounced in French, which I'm not even going to attempt. So International System of Units. It's also known as metric. So yeah, we can come up with an example such as 5 miles. That's fine. But in terms of actual measurement, in terms of calculation, unit conversions and so on, it's everything going to be in metric. We are not going to use any other system of units in this class. So as for fundamental units, those are not derived. Those just kind of exist by themselves, and then all the other units are based on these fundamental units. So some people say that there are, quote-unquote, 7 fundamental units. Now I'm putting 7 in quotation marks because some people say that there is actually 8. So I will show you all 8, but I'm not going to ask you to like count them, or not going to ask that question in the test. And in this class, we're not even going to encounter all of the 7, quote-unquote, 7 fundamental units. We're just going to know which ones are fundamental, which ones are not. So the unit of time is second. When I write the abbreviation for a unit, when it's by itself like this and not part of a calculation, I'm going to put it in square brackets, so then you know how that's just a unit of that measurement, of that quantity. And then, of course, if you're writing something like 5 seconds, you don't have to use the bracket. Next one is the unit of length or distance. You should know that one. It's called a meter, and abbreviation is little m. There is also unit of mass. You may be tempted to say gram, but that's actually not the case. It's kilogram. And the abbreviation is kg. So fundamental units is not the same thing as base units. Base units in metric system are all the ones without prefixes. We'll talk about prefixes in a few minutes. So most of the units that we're going to be dealing with in this class are going to be a combination of these 3. So that's what I mean when I say derived units. They're based on these 3. Like, for example, the unit of speed is meter per second. We'll talk about that too. Meter per second is a derived unit. It's based on meters and seconds. So that's what we're going to use mostly. We will also see the unit of temperature at some point. The unit is called Kelvin. Now, this is one of the ones that sometimes people say that's not a fundamental unit. Okay, so that's why, part of the reason why that 7 is in quotation marks. Now, notice how the word Kelvin is written with little k. So the unit is named after the person who came up with the way to measure temperature. So Lord Kelvin was his name. So notice how his name obviously would be capitalized because it's a person's name. The unit named after him is not capitalized, but the abbreviation is capital K. So that's true in a great majority of cases. If we talk about units named after people, and there are a whole lot of them, we'll see quite a few of them in this course. So we usually use abbreviated name with capital letter, and we write the name of the unit that's not capitalized. So we'll see that too. There are a couple other ones that we're really not going to see in this class, but we will see it in the next class. So this is the unit of electric current. Ampere is the proper name, although in the United States it's sometimes shortened to amp. Ampere was also named after a person who discovered it. So again, the name of the unit is not capitalized, but the abbreviation is. So we'll see that when we talk about electricity in the next course. This one here, unit of radioactivity. There is a bit of discrepancy there. Some people say it's Curie, named after Pierre and Marie Curie, who discovered radioactivity. And some people say it's Becquerel. So Becquerel was another person who worked with Pierre and Marie Curie, and he basically discovered radioactivity together with them. So again, some people say Curie should be a fundamental unit, some people say Becquerel should be a fundamental unit. So I'm just going to leave it at that. Again, that's not something that we see in this course, but we will see it in the next course. This one here is amount of substance. This one you have seen in chemistry. And the unit is mole. So the unit is written MOLE, but the abbreviation is MOL. Not much of an abbreviation, but that's how we use it. So we'll see a little bit of it in this course, and then mostly in the next course. And then finally, the last one is the unit of luminosity. So luminosity is basically a way to address how much energy is released by a star. It's related to brightness, but it's not exactly the same thing as brightness. Unit of luminosity is considered the fundamental unit, but you're probably never going to see it unless you're specifically going to study stars, and only from certain point of view. So this is called candela. Candela is Latin for candle, and it's abbreviated Ca. So again, that's not something you're really gonna see. Definitely not in this class. Definitely not in beginning physics classes. But since we're talking about all of the fundamental units here, it's worth mentioning that. Also, let's review some of the prefixes, SI prefixes, that we would use with this unit. There are a whole lot of prefixes. We don't need all of them, but you need to know at least some. Giga, 10 to the power 9. Mega, capital M, 10 to the power 6. Kilo, 10 to the power 3. Centi, 10 to the power -2. Milli, 10 to the power -3. Micro, that's the only Greek one. That's 10 to the power -6. And nano, 10 to the power -9. So the way that you would normally use it is something like this. If I tell you that distance is 1 kilometer, you would literally replace that prefix with 10 to the 3rd meter. Or if I tell you that mass is 5 milligrams, you would literally just replace that prefix milli with 10 to the -3 grams. Okay. There are a lot more, but these are kind of the ones that you need to know for this course. Finally, last thing I will tell you is order of magnitude. So order of magnitude is a rough estimate made by rounding off all numbers to 1 sig fig. And then of course you can have zeros and stuff after that, right? Because trailing zeros don't matter. For example, thickness of paper is roughly 0.1 millimeter. Height of a person is roughly 2 meters, or you can do 1 meter, right? So 2 meters is like a little over 6 feet. So roughly, right? So order of magnitude is never exact. It's an approximation. It's a very rough estimate, but at least it gives you an idea. Like, for example, if I say time frame is approximately 3 seconds, okay, then it's definitely different from me saying time frame is approximately 3,000 seconds, right? So we still use powers of 10. We can even say hundreds, thousands, millions, and so on. But we just kind of don't go into details describing all the other values and all the other numbers. Let me show you one other thing here. Is about unit conversions. We're not going to do a lot of unit conversions in this class, but the stuff that I did earlier was prefixes, powers of 10, right? So you need to know that. You need to be able to put everything into proper units when doing calculations. So proper units would be basically fundamental units. So if you ever see something that's not a fundamental unit, you need to convert it. Other than converting, like, say, hours to seconds or kilometers to meters or something like that, we usually don't encounter too much of that. There are going to be some other conversion factors that we'll see. Not too many, but once in a while. So just make sure that you know how to do that. The easiest way to do it is often referred to as dimensional analysis. If you have taken chemistry, I'm sure you've seen dimensional analysis before. So I recommend using this. If you have another way of making unit conversions, stick with what you know. I'm just going to do one quick example here to show you how dimensional analysis works. So for example, let's convert 3 years to seconds. So I'm always going to start with what's given, 3 years. And I'm going to multiply this by a factor that allows me to cancel out the units I don't want. I don't want units, I want seconds. But, oops, sorry about that. But I'm not ready to go to seconds yet. So the next step that I can do is to go from years to days. And I'm putting years on the bottom so I can cancel that. So that's my first step. I'm getting closer to seconds, but not quite there. The next conversion, I want to go kind of towards the next smaller unit. So we'll go from 1 day to 24 hours. And cancel out days. Better, not quite there. 1 hour is 60 minutes. Cancel hours. And then 1 minute is 60 seconds. Cancel minutes. So I can do this as many times as I want. I can multiply all of these conversion factors together. So this is in order to cancel what you don't want, you put the next unit of that kind on the bottom, or vice versa. So basically, you just want to have the units that you're canceling, one on top and one on the bottom. And once you've canceled out everything you don't want, then you end up with the units that you do want. Now, conversion factors. Do not count towards or against significant figures. Like I said, I don't really care too much if you always pay attention to significant figures or not. But if you did pay attention, then you would look at the number that was given, 3 years. So that's only one significant figure. So the number here should be rounded to one significant figure. I'll write the whole number, which I almost never do, because then what's the point of me talking about scientific notation and significant figures, right? But that's the exact number. So if I want to round it to 1 sig fig, yeah, I would write it as 9 times 10 to the power 7. Okay, so like I said, I don't care too much. I think that rounding things to 1 sig fig is overkill, unless you're doing just a really crude, rough order of magnitude estimation. So I kind of like 3 sig figs, just in general. Conversion or not, doesn't matter. But kind of use your good judgment. If you ever have 2 significant figures or 4 significant figures on a calculation, it's really not that big of a deal. If you don't follow sig figs rule, it's really not that big of a deal. Just don't go crazy on writing down the number of decimal places. Like that number that I wrote, 946080000, please don't do that. That's just a waste of time. And one other thing, when putting numbers into your calculator, make sure that you don't round too much. So when you're doing a calculation, you get an intermediate result. On paper, you would write down your intermediate result was, whatever, 3 sig figs or something like that. But store that exact number in your calculator if you're going to use that number for a subsequent calculation. So for example, here, if I needed that time that I calculated, in the next calculation, I would not use that final result. I would not use 9.9 times 10 to the 7 seconds. I would use the exact answer. So all of you have calculators. So all of you know how to use them. All modern calculators have a way of storing, copying and pasting, or any other method by which you can refer back to the exact number so that you don't round answers. You don't get too much round off error as you go along the way. So keep that in mind for basically all of the calculations that we're going to be doing in this class.